no reasons for that.
Yeah.
The only class I've ever had in there.
Yeah.
Taking the survey. The class I probably will have in there is data. Guys, there's an extra survey with Dr. Slow, which is an absolute joke. Oh, it's really good.
I took it like 11 people.
Okay.
Oh, I can see that.
Welcome back, everybody.
And I'm like,
Today's a Friday.
I thought it was the diameter thing, and I put with the fact that it's
Okay.
hilarious.
So no one's online, everybody.
Switch it to
All right, so let's just get started with in-class attendance. Okay, everyone.
First time this semester. I'm here and there. And he actually walked over so now he wants to
No, I wouldn't. No.
I knew something was changing.
No, I won't.
I'm putting it like almost all the time. He's no longer a house. The thing is, been shoving my backpack so much, if I lift it up, you can like see how the marker has. Yeah, I think it's pretty cool. You can like kind of read it, even without.
So let's begin with updates today.
Update.
There are a few new updates I posted yesterday, which is essentially something you already know about midterm exam 1, which is coming up next Wednesday. Wednesday, October 13 will be your first midterm exam 1. Materials covered will be A1 to A4. Today we're going to start A5, but it's not going to be included. Okay. And then, of course, it's 15 minutes in class and cross book and notes. You can use your calculator, but not the device, of course. Because all the solutions are posted. If you have a laptop, that means you can access to all solutions. That's one exam, if so. Your cell phone, too, of course, you can access to all the solutions. Go ahead.
On Monday, will we be reviewing for the exam or still?
Not really, because solutions are all posted. I don't feel like I have to review. Okay, anyway.
Is there a certain type of calculator we're allowed to use? Or
Is that what you want to use?
Yeah.
That's fine, that's calculator.
Okay, cool.
Yeah, some graphing calculator is calculator.
Okay.
Can you like a custom coded every solution into it?
If
Possibly, if you spend a
10 hours
huge
on it,
amount of time,
but
yeah, but
it would be
anyway,
no-
you're probably not gonna do it. So
Yeah,
So I assume that, yeah, it's easier to study than just a custom built code and everything and try to hide it all the time. That's not much, yeah?
okay.
Okay.
Yeah.
Yeah. But this is not the calculator, of course you know. Don't use this and claim, oh, this is calculator. No,
I mean, is it very?
this is a device.
No. Actually, is it for fluids last semester?
And I already told you 3 problems given. And I'm going to probably start making the problem by cut and paste from somewhere and then just to change a little bit, tweak a little bit, try to make you feel confused. Oh, this is not the same problem I saw. Yeah, of course it's not, but it's going to be the same kind of problem, which I took it kind of thing. So I guess the bottom line is memorization never works in this class unless you fully understand, master the concept behind it. I don't think you can do it. Memorization, well, I mean, this is engineering. If you try to memorize and passing an exam and going through it, you're going to hit the wall. This is probably the very thick wall right here. If you try to do that. Anything, any question about this exam? I hope everything's crystal clear. Okay? And here, this is something you probably don't care until like you come back from fall break. But anyways, quiz 6 is posted. you can start take a look at it. This could be a fun thing to do during the fall break. I don't know.
Yeah.
I don't know. Because this is due Wednesday, not even Monday after fall break. So you can, if you want to, you can forget about it. That's fine. I just paused it. Okay. So this is something we are going to start talking about it today. Unit A5 is all about aerodynamic coefficients. We don't talk about actual forces. We don't talk about actual pressure. We turn everything into coefficients. Why is that kind of thing? Everything's coming from here, this concept, similitude. Okay? So this is something you have to go back and review and understand and get the fundamental concepts from fluid mechanics. Okay. Go ahead, question?
And so the homework is due Monday,
What homework?
4.
Oh yeah, it's here. I mean, I thought it's already announced last week. Right. Yeah, F4. Oh, this is also new? Oh.
You announced.
Oh, sort of new, okay.
It's new because we didn't have it on Wednesday. We got it Wednesday night.
Okay,
Yeah.
yeah. So, sorry about that. So this is considered sort of new. So homework of unit A4 is due Monday, Newtons. If that's your question, yes. My answer is yes. That's right. This is going to be part of your exam. Of course, you have to do it. Go ahead.
So after we submit it on Monday,
Yeah.
will you have the solutions posted? So
Yes, I post the solution before I start actually grading.
Well, yeah.
So, yeah, so as you submit on like Monday noon, right?
Yeah.
Then Monday I have a class until 3, right?
Yes.
After that, I'll probably start grading.
Oh,
So
okay,
by
I was
3
thinking
p.m.-ish, you can access to the solution.
I was worried like the exam would come and we wouldn't
Do-
have the solutions.
If
That's
you
fine.
want the notification, I'll send you email saying, hey, now solution's all up. Go ahead, study for it, kind of thing. I'll do that.
That would be nice.
Okay,
Yes, thank you.
I'll do that.
Yeah.
Okay, sure. Any other question? Although it's only 5 problems, and then unit A4 is kind of simple problem. It's an ESP. Either use Bernoulli or an energy kind of problem. So should be able to do that. Any other question? Good. So today we are going to get into unit A5, aerodynamic forces and moments. So this is probably the beginning of actual subject of aerodynamics. So we are actually getting out of all the review phases of fluid mechanics kind of thing. Fluid mechanics review process is quiz 0. Once you go through all the programs of quiz 0, program 1A, 1B, all the way to 6, which is total 7 programs. That's quite a bit of work. It is essentially cut and paste from my final exam of my fluid mechanics class anyways. So you're supposed to solve all of them in 2 hours if it's final exam. So you're spending until like October doing all of those. But those are quite important fundamental concepts. You definitely need to master everything before you actually start understanding aerodynamics concept. That's why I've been doing that. Okay, so you have one more quiz program to go. And also quiz 7 is actually coming straight out from one of those aerodynamic forces moments thing. In other words, next semester or so, you start taking experimental aerodynamics class, which is a wind tunnel testing. Now, one of those testing will involve measurement of the surface pressure distribution. Putting lots of pressure taps on the surface and measuring pressure distribution on the surface. Why do you do that? Well, of course, you can compute lift and drag out of it, or lift and drag and also pitching moment out of those surface pressure distribution, because that is essentially the mechanism why airplane can have a lift and drag and moment, pitching moment around it. Everything is driven by surface pressure distribution. So wind tunnel testing, obviously, oftentimes come with pressure distribution measurement. Now, how can you pick up that data to actually resolve into lift and drag and pitching moment? It's something, the central theme of this A5, so don't miss it. And then quiz 7 is going to basically conclude that. Okay. So when you start taking wind tunnel testing, do a surface pressure measurement. Now the professor says, okay, go ahead, find out lift. Oh, lift? Well, we measure the pressure. How can we get a lift out of it? Well, you should know from N1. Yes. So this is the unit. Okay. So let's begin with page 1. So what is the source of all the aerodynamic forces generated. Let's take a look at the cross-section of a wing to begin with, okay? We are going to start our discussion on 2D. Now, once we understand the mechanism on 2D, three-dimensional model is essentially stretched out to 3D space. In order to design an airplane wing, you have to start with a cross-section that actually create the wing to begin with. Otherwise, you cannot predict anything. You can create the wing with series of different cross-sections or single cross-section. Have you ever heard of chocolate bar wing?
Hershey bar wing.
Hershey bar wing, yes. That's a constant cross-section. This kind of chocolate bar wing, that's right. Hershey bar wing. It's not my name. Sounds rugged, but Hershey bar wing. You don't need any brain to design that kind of wing. That is Cessna 172. That's that. Here we go. Okay? You don't have a taper, you don't have anything, but it actually has a twist though. The wing is always twisted. Okay? We're gonna discover that later. But two things is the source of lift and drag and moment. Let's take a look at cross-section of wing. This is called airfoil. Let me just write it down here. I hope this doesn't show me blue screen. Let me connect up. Oh my goodness. Don't die on me, don't die on me. Okay. So this is called airfoil. Okay, now it's working. So this is 2D cross-section of a wing, okay? Okay, good. So we begin our discussion of cross-section of a wing. Wing can be like a variety of change of cross-section across the span from root to tip, or it could be the same cross-section from root to tip. But anyways, at each cross-section of a wing, you're going to have two things. One is, of course, what's this? P.
Pressure.
This is the surface pressure distribution over the surface. I mean, well, I said something funny. This is the pressure distribution over the surface, or surface pressure distribution, either way. It's not like a surface pressure distribution of the surface. It's like a redundant. Anyways, so what's this anyways? This is a normal force divided by some kind of difference area that is called pressure. Pressure is normal stress acting on the surface. That's what it is. If you took like surface mechanics, you have two different kinds of stresses, right? One is normal stress. The other one is shear stress, of course. So those are the normal and shear forces divided by some kind of difference area. Could be any area. That is going to give you two information. One is the pressure, which is distributes over the surface. The other one is shear stress, distributes over the surface. Now, in aerodynamics, one especially, if we introduce a concept of inviscid, have you ever heard of inviscid? What is it?
What is it? The shear, the
Inviscid.
there's no boundary
For a
layer.
moment, let's just ignore the presence of viscosity, because viscosity is the one creating shear stress. Do you know the equation for that? From fluid mechanics? What is it?
Tau
equal to?
mu dy.
Mu dy, no, mu what? dB what? dB dy. In other words,
Yeah.
because of the presence of viscosity, the velocity on very close surface to the wall is going to be a function of height. Zero on the surface. No slip condition. Do you remember that? Right here on the surface, velocity is zero. And the velocity gradually increases over the thin layer called boundary layer. Then becomes the velocity externally flowing. For a moment, we can completely ignore that existence of that boundary layer because of zero viscosity. That is called Euler's equation, by the way. So if you use the Euler's equation to solve and analyze the flow field, how is zero? So we completely ignore the existence of this thing. We only take a look at pressure measurement. That is what the wind tunnel test is all about. You're going to put the pressure tabs, tap into the pressure information, but you can never measure this kind of thing. So we purposely ignore that. So low-speed wind tunnel testing of pressure measurement is essentially implicit assumption. Okay? But theoretically, we can, of course, include shear stress distribution of a surface. Now, we are going to do that for a moment, because this is theory. So at any location over this surface, cross-section of what we call airport, at every location, you have two things happening, pressure and shear stress at every location. And then we are going to keep track of that distribution using the coordinate S. Have you ever heard of S coordinate system? What kind of coordinate is this? This is called streamline coordinate system from fluid mechanics. So you are taking streamline, comes right into the stagnation points, right over the surface, flow away. That is called stagnation streamline. We're going to cover that in this class later. So let's say this upper surface and lower surface taken as a streamline, and then it's a coordinate. It's called S coordinate. It's a coordinate system. You happen to take this surface as a coordinate system, then represent this location, and then at this location, let's say point A, location SA measured from this leading edge. What is the pressure here, PA? What is the shear stress here, tau A? And then, of course, in wind tunnel testing, if you create the surface pressure tab, you can, of course, at least measure PA at this location, right? That is something you are looking at this picture. Let's take a look at this picture here. Okay, updates of last months. Wind tunnel lab. So this is what you're doing. Okay, if you really zoom into this model, you have a bunch of surface pressure tabs. Each one of them is connected to those tiny tubes. Each one of them is connected to the particle manometer. What are you measuring? Because you want to measure the surface pressure distribution. Okay, this is one of those required testing, and then you really, of course, you need to know why you're doing it, obviously. Okay, so let's just go back here. So next thing, after you measure pressure and shear stress, question over, at least you measure the pressure in real wind tunnel testing in those. You're going to, what are you going to do now? You are going to have a pressure distribution over the surface, shear stress distribution over the surface. You're going to integrate from leading edge to trailing edge on both upper and lower surfaces. You're going to come up with a resultant of two things. This is a resultant force, resultant moment. Have you ever done that in studies?
Sure.
Yeah, you did that. Distributed loading, you find out resultant force, resultant moment. Right here is something called center of pressure. No, it's not. It's not. No, it's not. This is like an arbitrary location anywhere. You can choose any location along this line. Okay, let's just define that line. Okay, you can draw a straight line. Okay, you can draw a straight line connecting from leading edge. Let's say this is called leading edge, L dot E dot. Aerodynamics technical term. You can always use that in front of your parents, and parents don't know what you're talking about. This is trailing edge. You can connect that leading edge to trailing edge with a straight line. Assume this is straight, okay? This is called chord. Chord line, okay? And then length of the chord is called chord. We oftentimes use C, chord, okay? All right. So you can choose any location along this chord line, any location. And then you can determine resultant of force and resultant moment at any location. That's the beginning of our analysis of 2D airfoil aerodynamic forces moments. Okay. Now, let's say you choose this arbitrary location. This is the resultant force. This resultant force can be resolved into any two directions. It's a vector calculus. If you resolve this resultant force into the direction of the chord, and the direction perpendicular to the chord, it's called axial force and normal force. Of course, it's naturally coming from the direction. So this is called normal force, okay? This is called axial force. Okay? And here's also more common sense in terms of aerodynamics. Oftentimes, if you're doing aerodynamics, you're going to resolve this into two directions, which is relative to the incoming free stream. Relative to the incoming stream, free stream, okay? Incoming free stream, you can resolve this resultant force into the direction parallel to and perpendicular to this incoming free stream. This is actually called drag. Oh, this is more or less like the aerodynamic term, drag. And then lift, okay? Because you want to talk, relatively speaking, from the perspective of airplane. Because airplane is always opposed against the free stream. So suppose if you want to have more lift and less drag, you are happier, right, as an airplane designer. So this is lift and drag. You can resolve this resultant into two directions, which is incoming free stream. This is the free stream, of course. Okay. And then something, the angle between free stream to the direction of this code line, alpha, okay? So this is quite important terminology in aerodynamics. Alpha is called angle of attack, AOA. Okay, angle of attack, AOA. I don't know what's the origin of this word, but it could be like World War II dive bomber. Angle of attack, I don't know. That's my assumption. Because you're diving, attacking, dropping bombs, dive bomb, I don't know. I really want to ask that kind of question for AS major students, if they know it or not. So you have a relationship between those two different kind of forces. One is normal force and actual force. Normal force and actual force. You're going to take a look at the angle of attack for cosine and sine components and add or subtract each other to have a lift and drag component. So there's a relationship between those two different kind of forces, lift and drag versus normal and actual forces. One is called body attached coordinate system. The other one is, of course, inertial coordinate system relative to the airplane. Body attached coordinate system is quite important because when you do a wind tunnel testing, that is something you have to deal with. Normal force and actual force, those are essentially attached to your test rig in wind tunnel. So you have no choice. If you run wind tunnel testing, those are the only forces you can measure. You can never ever directly measure lift and drag, forget it. Okay, when you run wind tunnel testing, you can only measure the body attached coordinate force components, and then knowing that angle of attack, you can resolve lift and drag. That's what you do. Okay, so these are body attached components, force components. Okay, so those are the actual values, force values you actually measure using the devices inside of the wind tunnel, something called balance system. Balance system measures normal force and actual force. Together with angle of attack, you can resolve into lift and drag force components. Okay. Now, there are two different ways of measuring lift and drag in wind tunnel testing. Let's just go back and take a look at once again. So if you take a look at wind tunnel, you have two different ways to measure aerodynamic forces. One is a direct measurement. Suppose if you attach this test, what's this? This is, I'm not sure how do you attach this thing. This thing is attached to the side. Well, there's no device attached to actual force measurement. So in this case, your test, the purpose is measure the pressure. That's the only thing you can do. Now, suppose if this is attached to some other device, something called balance system, that actually measures the force created in certain direction, which is direction parallel and perpendicular to the code length. Code of your test. This is a test model. So those two things, one is a direct measurement of force. The other one is a pressure distribution measurement, and then you can resolve into force components later. Then you can compare those two. Okay? So let's move on next page. So we are going to actually start here. We want to define something called coefficients because this is aerodynamics class. I will never talk anything real. Well, what do you mean anything real? Anything real means how tall you are. I don't know. 6 foot? Well, we're not going to talk about 6 foot. We talk about, okay, so what is it? 6 foot divided by chord lengths. Okay, so I have lengths divided by chord lengths equal to 1. That is, you are here. Height divided by chord length 0 is you are here. So my height is 78% chord length, whatever it is, normalized. So everything's normalized. That means there's no unit associated with in aerodynamics, no matter what you talk about. You're not going to talk about lift in aerodynamics. You talk about lift coefficient. You're going to talk about drag or moment in aerodynamics. You're going to talk about moment coefficient, drag coefficients. You're not going to even talk about pressure. You talk about pressure coefficients. You're not going to talk about friction. No, it's a skin friction coefficient. You're not going to even talk about x distance. No, you're going to talk about percent curve. Okay? So what's the location right here in the halfway through of the chord line? That's called 50% curve, measured from leading edge. There's no unit associated with. Okay? Because it doesn't matter if this is 1 meter or 2 meter, 10 meter or 1 millimeter, it doesn't matter. 50% code is 50% code, regardless of your size. So everything's normalized. We need to do that because oftentimes airplanes are tested in smaller scale in wind tunnel and then predict larger actual airplanes performance. You cannot actually talk about something that comes with units. What is the concept of that? Anybody, please tell me. Some fluid mechanics. What is this concept? Similitude. That's the quiz 6. Okay, so make sure you understand the quiz 6. Quiz 0 program 6 to begin with. Quiz 6 is all about similitude. Let's understand the concept of why we're doing this. Okay, we're not going to talk anything with units. Why is that? We're not going to even talk about what's the airspeed of wind tunnel testing today. Well, I don't know, but I know the Reynolds number. What is it? Because Reynolds number is unit rest. Airspeed is feet per second, miles per hour, whatever it is. We're not going to talk about those things. Okay? Right.
Is the reason why we use similitude?
Sorry? Reason why?
Similitude,
Yeah,
you know,
reason why.
Yeah, is the reason why we use it so that like
That is
you can scale.
mechanics.
Yeah, so you can scale a prototype to the actual.
That's what
Model.
it is. Essentially what it is, but that's fluid mechanics. So that's important for you, okay? So take care of the quiz 6 or quiz 0 program 6. That is essential. Very essential. Okay. So let's talk about coefficients. Something called lift coefficient, drag coefficient, moment coefficient. Okay. You have actual force lift, which is a force resolved perpendicular to the incoming free stream is a lift. You have to normalize it. That means divided by Q and S. What's S?
Wing area?
Isn't it surface area?
What is wing area?
Isn't it?
Okay, go ahead.
Is it your chord times your length or your
Chord times length could be.
Is it just the bird's eye view?
Bird's eye view,
So 2D cross
could be.
Like the platform area, you mean?
It could be.
the chord.
It depends.
Yeah.
You know, you have to be very careful about that. You may come with some idea that, okay, so this is called characteristic area. What is that? Characteristic area. What is it? You can choose whatever that it means. That's what it means. Depending on your application. If it's airplane, somebody made a decision, okay, let's take a look at bird's eye view. So this is code. But suppose if it's parachute, or the parachute deployed, what is the area I can see from up front? It's the frontal area projected. That's another area used for parachute, even though we're talking about drag coefficient, same meaning. But this area could be different depending on your application. So this is called characteristic area. Be careful about that. Every time when you use S, this S could be defined differently. It could be defined differently from different country. Russians may use different meaning of area than Americans. I'm not kidding, okay? So be careful about that. That's the meaning. So you can choose any area you want. But in aerodynamics, of course, we are going to use projected frontal. For the drag producing device, it's projected frontal. We're going to cover that later, okay? Just to stay tuned. So those are all characteristic area. Characteristic area. Okay. So one thing you have to be very careful about is the moment. Moment is called pitching moment. In other words, this moment. Airplane pitch up, pitch down, this kind of moment. Now, you can take a moment just about any location around the code. Okay? You can choose to measure the moment at the location here. What's this location, by the way? Can you see it? What's this?
Quarter chord.
Quarter chord, this is C/4. This is typically called quarter chord location. Quarter chord is kind of common choice for aero. We're going to find out why later, okay? This is for quarter chord. Quarter chord. Very common choice. Suppose if you want to choose a half chord and then determine moment developed at the half chord location, is it going to be the same body?
No.
It's going to be a different body because the moment is developed at each location is a result of resultant moment, right? It depends on the pressure distribution. When you pitch up and pitch down, pressure distribution changes. That actually changes everything, lift and drag and moment. And then if you choose this portion and this position, this position, this position, that position, it's going to be all different body, even though you're talking about same angle of attack. So moment depends on the location. So when you say moment, moment should come with a location specifier. This is important. Don't forget. So this is a moment comes with a specifier. In other words, if you're talking about moment, is that the moment at the leading edge, moment at the quarter curve, moment at the half curve, moment at the trailing edge, you have to tell location with it as a subscript. So moment and moment coefficient should always be associated with some kind of subscript telling you the location along the code. This is a moment taken at the leading edge, taken at the quarter curve, taken at the trailing edge. Those are all different bodies. Okay. Go ahead.
So if it's a moment taken at the leading edge,
Yeah.
would the chord length be zero?
Code length is 0, yeah. That's right. Yeah. Okay. So that is 0% code location measured at the leading edge is leading edge anyways. That's right. 100% measured from leading edge to trailing edge. Quarter code is 25% measured from leading edge to quarter code. Okay. Something like that. Okay.
Just double checking, that's what the C is, right? Is that the C in the equation for?
Oh, C in the equation, good point. I appreciate that. So this C is what? This is chord length.
Oh.
Yeah, chord length is length of the chord. This is C. Because moment is a force times some kind of length. In order to normalize it, you have to divide also by some kind of distance. This is also called characteristic length. Now, in aerodynamics, we commonly choose the chord length as a characteristic length. This is, again, characteristic length. So in order to normalize the moment, you have to divide by Q and the area and the chord length. Okay, that's a good point. Go ahead.
Is this overall chord length no matter where you're taking your moment, or?
This is, again, we're talking about assuming that the chord length is constant. It's like
Right.
a Hashi-Bar wing.
Yep.
Suppose
Yeah.
you design this kind of wing. Typically, you have to take a mean aerodynamic code.
Okay.
We're going to talk about that in flight mechanics class.
Fine.
Yeah, we need to find out what is the mean value of the chord lengths of a complex designed 3D wing. Okay. And then it is a function of Mach number also. It's kind of complicated. Okay. So suppose if we have a chocolate bar wing, everything is super easy. Let's stick with it for a moment. And then we can always make things more complicated easier later. So, okay. Any other question here? So those are just the basics of lift and drag and moment coefficients of aerodynamics. Okay. So be careful. We're not gonna probably talk anything with units. So everything is dimensionless from now on. Okay. So next is the difference between airplane, such as lift producing device, compared against what's this? Like a huge circular cross-section pillar at the Daytona Beach campus. Then, unfortunately, 10 years ago, when hurricane hits that pillar collapsed, and then building is damaged, and then lost by 5 airplanes. I don't know. It actually happened. So the purpose of this thing is this doesn't create any lift. It only creates the drag flow of a circular cylinder kind of thing. So anyways, when you try to find out lift and drag and moment coefficient, you have to divide somehow with area S and range. This is a characteristic range. Okay? So characteristic area and range depends on your applications. If you are talking about airplane wing, this is called projected planform area. You are going to drop your airplane to the ground. Take a look at bird's eye and how much area of your wing you can see. This is called projected planform area. So you're going to use this S projected planform for all of those S meaning. In other words, CL, CD, CL. S means if it's airplane wing, it's a planform. Okay. Now, all of a sudden, suppose if you're doing aerodynamics of a parachute or drag producing device, you are going to all of a sudden use a different definition of this area. This is called projected frontal area. Okay. So that's the meaning of this area S. What is a projected frontal area? Suppose you have, I don't know, circular cross section, like a building pillar placed in a free screen, like in a smaller scale, something like this. This is a building pillar, cross section circle. Air is flowing. It only produces the drag. Okay. So what is the area S you're going to pick it up? This is the area you are seeing. Diameter times length. Projected frontal area. Okay. And also parachute. Also, when you deploy the parachute, how much area do you see if you see from front? Called projected frontal area. That is going to be the meaning of area S here, for all the lift and drag moments. So the meaning of S depends on your application. Be careful about that. Go ahead, Stephen.
Since that's like a 2D like circle.
2D circle, yeah.
Then there'd be no projected frontal area because there's no length, right?
No length, yeah, that's right. It's just basically area.
Okay.
Area you see. This is area you see. You see only rectangular shape. Diameter times length. If this is this case.
Yeah.
Okay.
Yes.
Yeah, that's right. That's the area. Projected frontal. If it's parachute, it's a circular area. If you see it from front. Now, you have to be very careful. Once you define this area S meaning, you have to use it throughout. So if you're talking about airplane, S means planform, planform, planform. Throughout. You need to be consistent within your application. You cannot all of a sudden change it. Okay, for lift coefficient, I'm going to use planform. Drag coefficient, I'm going to use frontal. You cannot do that. It's a big no. Okay? So you have to be consistent within your application. Okay. And then this area, this length L. This L is characteristic length. This is almost always, in case of airplane, it's a code length C, right? Now, in this particular case, drag producing device is going to be dynamic, right? Flow over circular cylinder, length L is the diameter Have you ever seen that kind of stuff in fluid mechanics? I hope so. Go ahead. Yeah, go ahead. Anyway.
So, for the coefficient of moment equation, we use the chord length, but in an example where the chord length changes, do we only use the chord length for that given spot?
Again, chord lengths need to represent the wing. If the wing doesn't have a constant chord length, you have to pick up mean value.
Okay.
So that's sometimes called like a aerodynamic mean aerodynamic code, MAC. So we cover that in front again. Now let's assume for a moment, if it's 2D, this is chord length, and then if it's a wing, this represents like a mean value of the code. If it's a variable, okay, some kind of mean value, best representing this wing. Okay, anything else? Go ahead.
For our drag producing device,
Yeah.
what if it was instead of being a circle, it was like a brick where it has 2 dimensions associated with it?
Still, projected frontal area.
Okay.
That's right. Now, this length is questionable. I don't know what it is. It depends on the type of device you're talking about.
Okay.
Yeah. It's usually diameter. If that's this kind of thing. Suppose if it's a parachute, I don't know. It's still probably be at diameter.
Sure.
In the case of a rectangle, would you use width or length?
What's the rectangle?
Like instead of a circle where you just have one diameter everywhere?
Again, it's still projected frontal. So if this is rectangle.
Yeah, but what would you use as your L value?
L value is, I don't know. Again,
Would
it
you use
depends
the
on
length?
the application. We have to carefully be consistent with that application. So if somebody's designing, I don't know, a concrete brick with aerodynamic drag, I don't know, I've never heard of it, but if that kind of study is ongoing, that community uses this is the characteristic length you have to follow through. That's exactly what we're doing. So airplane design, of course, people use code lengths and then frontal projected transform for everything. So we have to be consistent within that community. Anyways, so let's talk about, okay. So anyways, so this is quite important. So projected surface area characteristic surface. So the meaning of this characteristic surface is this is some kind of surface that actually best characterizes your device's most desired character, which is, in case of airplane wing, it's a rift, of course. Rift is what you're interested in. So in order to normalize that rift value, what is the best way to normalize? Of course, it's a prime form. Now, if you're talking about like a, I don't know, parachute, that's a drag producing device. What is the best surface to characterize that kind of drag, which is, well, how much area you see, because that's going to have the most impact on the design of parachute. Okay. So be careful about that. That's one thing I would say, because by the end of the semester, people forget about it. And then if the final exam, all of a sudden I say, okay, so what is the drag coefficient of this device? People use, oh, it's a prime form, right? No, this is a projected frontal. People forget about it. Be careful about that. Okay. Let's talk a little bit more about airfoil. Okay. This is the concept of airfoil. So usually we are going to start with our discussion or design process of airplane starting from airfoil. Airfoil is a 2D cross section of a wing. Now you can design very complex shape of wing, which is every cross section is unique kind of wing. You can of course do that, but at the same time, if you want to do such a thing, you need to understand the character of every single different unique cross section's behavior before you do such a thing. Okay, 1 more minute. Yeah. So let's just redefine once again. This is the concept of airfoil. So let's say you have an infinite span of a wing, hypothetical, okay, with a constant cross section throughout. If you cut out a unit length of that kind of wing, in other words, this is the unit length of a wing span. This is the cross section which is constant across this unit span. So you have a wing, you chop off this unit span, assuming this is a constant cross section. That is airfoil. So that means whatever the lift you produce out of this unit span, whatever the force divided by the span is going to give you lift per unit span value. we are going to use this notation. L prime. This is lift divided by span of a wing. Span is a beat, okay? Span is a wingtip to wingtip distance from here to there, wingspan. So lift divided by wingspan is a lift per unit span. What's the unit? Newton per meter kind of unit. Pounds per inch by kind of unit. Pounds per foot kind of unit. Drag also. This is the drag divided by span of a wing. Moment divided by span. Those are the per unit span value. That's airfoil, okay? This actually defines the two-dimensional coefficients. Two-dimensional coefficients is lift per unit span normalized by Q infinity S. Now we are talking about this kind of wing. Unit span and code. So what is the area S become? Area S becomes code times unit span, which is C. L prime over Q infinity C. This is called airfoil 2D lift coefficient. Same here. This is an airfoil 2D drag coefficient. This is airfoil 2D moment, pitch moment coefficient. Now, in order to differentiate from actual wing to the 2D airfoil, we are going to use both lowercase. So lowercase means 2D airfoil coefficients. We are going to always start from there before we build the 3D wing. Go ahead.
When you say wingtip to wingtip, are we ignoring the fuselage?
That's right. For a moment, yes. Yeah, because fuselage, if you add the fuselage, it always complicates issue. Because is it part of the wing or not? I mean, usually not. So, okay. So let's be careful. Today's lesson, uppercase and lowercase, those are pretty different definition of coefficients. Uppercase is wing, 3D wing coefficients, lift and drag mode. Lowercase is two-dimensional airfoil coefficients, lift and drag. Okay, let's just take it from here to home today. And then have a great weekend. We're gonna see you back on Monday. And we're gonna pick up from page 4.
Did I hear a structure?
Yeah, I've done problems 1, 2, 3, or 4.